All right, hi everybody. We are going to take a look at a free fall example problem. This is actually one that says, okay, some kid is testing out a new iPhone app, kind of like the one we talked about in class, and they throw their phone in the air upward at 25 meters per second. Now, assuming that there is just negligible air resistance, there's a series of questions they ask us about it. How high does this thing go? How long is it in the air? How fast is it going just before the student hopefully catches it at the bottom? So in order, when you're approaching these kind of problems, there's lots of different strategies to take a look at. I'm going to start with drawing a picture just to try to make sense of what's going on with this particular problem. So let's think of this in terms of here's the kid down here, and they just throw this little thing, this cell phone, and what would it do? Well, it shoots up with a certain velocity, and as it gathers height, its velocity gets smaller and smaller and smaller and smaller and smaller, and then what happens at the top? Well, it's got to stop, right? And then it will start its journey down. So I'll just kind of draw a little symmetric diagram here, and then this guy's heading down, and then at the bottom, at the same height that it started at, it's going fast too. So we want to choose a direction here that makes sense for us, and I think it's a pretty good idea to choose upward to be our positive direction. So imagine our zero part of our meter stick starts right where he lets go of this cell phone, and it just goes up, 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 all the way up to its maximum height. So what are the things that we know? Well, we know a variety of things. We know that this thing has an initial velocity of 25 meters per second. And in fact, we can remind ourselves of that by putting a little VI here. So, and it is upward, and because it's upward, I can remind myself by that if I want to, and put a little plus sign there. Well, what else do I know? There is something else that we know, that we can just look at this picture and think about this situation. We can think about what velocity it's going up top. Actually, at the top, we know it is stopped. That's a little bit of extra information that could prove useful to us. And one of the most important things when dealing with free fall motion like this is to remember that this thing has an acceleration downwards equal to little g, or in this case, since we took down to be the negative direction, negative little g. So that's going to be negative 9.8 meters per second squared. That's going to be really important when we start using our formulas. So what are our formulas? Well, I like to write them all out when I start problems like this so I can have them on hand easily. So final velocity equals initial velocity plus acceleration times time. Final position equals initial position plus initial velocity times time plus 1/2 at squared. And then the third one, final velocity squared equals initial velocity squared plus 2a times the change in position, x final minus x initial. So these are my three biggies. I can think of it as 1 and 2 and 3. Okay. So that is sort of my given data. What do I want to do with this? How high does it go? So we want to know at the top here, what is its final position? That's what we want to know. So let's think about this. The ball goes up, or sorry, not the ball, but the cell phone goes up and the cell phone comes down. Let's just focus on the up part. Okay, so imagine you got your meter stick. This thing is launched with an initial velocity of 25 meters per second, and up here at the top, it will stop. I'm going to call this my final velocity, because this is the part of the motion that I'm concerned with, and then this will be my initial velocity. And of course, the whole time I got to remind myself that acceleration is down, and it's negative 9.8 meters per second squared. So when I'm looking at this, I'm thinking, well, I don't have anything about time. And if I notice, my first two equations have stuff about time in them. So let me grab that second equation. Let's see what it can tell me. Final velocity squared equals initial velocity squared plus 2 times acceleration xf minus xi. Well, I know that the final velocity, meaning at the top, the velocity is 0. So I can put 0 squared, but it's going to be 0 squared would be 0 anyway. My initial velocity, what I start with, 25 meters per second. I'm going to leave out the units just to make it a little more readable. My acceleration is negative 9.8, and yes, you definitely need this negative sign. It's not going to work otherwise. You'll get wacky answers. And if I consider my initial position to be equal to 0, then I'm just going to have x final minus x initial, so I'm just going to have my x final there. And if you notice, a bunch of numbers and one unknown, one variable. So that's what I want to solve for. So let me go ahead and do that now. So x final, it turns out when you do 25 squared and then divide by 2 and divide by negative 9.8, because you brought this over to the other side, you're going to get 31, a positive 31.9 meters. And if you think about it, that makes sense. Positive, meaning it's going to end up higher than it started, not below it. That would be a little weird. And about 32 meters, so that's a heck of a throw. That's a pretty good throw. Okay, so that was the answer to, that's number 1. That's number 1. What else can we do? Well, let's see. The second thing it was asking us was how long is it in the air? So we're still looking at this upward trajectory. Now this is a little bit trickier, because how long is it in the air? Well, you throw this thing up, and what does it do? Gets to the top, stops, falls back down, and then at the bottom, maybe you can convince yourself that it's going just as fast in the opposite direction as it falls down. So it's kind of, there's a symmetry here. Do you see that there's you know, as it goes up, and it's going to be kind of doing the same thing as it comes down. In fact, the journey that it has from the bottom to the top will be half of the total time. I'll use t with the little 1/2 there to remind me that it takes half the time to get from here to here as it does for the whole journey, and half the time as it falls down on the back side. So that's going to mean that it, if I can figure out what one of these times is, I can just double it, and then I will have the entire time that it is in the air. So I'm going to remind myself with that. I'm going to write t, my total time is 2 times t to the 1/2, just to remind myself. Just to remind myself that this t 1/2 thing is half the time. So let me think. I bet I can find this t to the 1/2. Why? Because I have an initial velocity here. I have a final velocity of 0 at the top. Let's take a look at this. So I can say initial velocity is 25 meters per second. Final velocity is 0 meters per second. So I have v final equals v initial plus acceleration times t with a little 1/2, just to remind me that at the end I'm going to have to double it. And my final velocity at the top is 0. My initial velocity is 25. My acceleration is negative, whoopsie. My acceleration is negative 9.8. And yes, 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 you need the negative sign. It won't work without it. And when you solve this, you know, subtract 25 from both sides, divide by negative 9.8, and I get a positive time. That's encouraging. I don't have to do any time traveling. And t 1/2, half the time, is 2.55 seconds for this problem, which means my total time, which is 2 times t 1/2, is about 5.1 seconds. Now, there's another way you can do this. The other way you could do this was to say, let's not have our final velocity be up here. What if it's down here? What if it really is the whole journey? What about my final velocity here? Well, this actually kind of goes into question 3, which is, what is the final velocity of this thing as it falls? Well, maybe you can convince yourself that there is a symmetry going on here, and it turns out that this final velocity is equal to, in magnitude, the initial velocity. It's just in the opposite direction. So our initial velocity was 25 meters per second, so this final velocity, meaning the velocity that it has here, just before it hits the guy's hand, before he catches it, is going to be negative 25 meters per second. All because of what? Because of symmetry. This is a symmetric situation. And it's symmetric because there's no air resistance. If there was air resistance that it's fighting the whole way, it wouldn't work. It wouldn't be quite the same way. But I think we're good. Now that brings up an interesting idea. What if I just wanted to find number 2 using this number? Well, you could. You could have an initial velocity being 25 meters per second, but the final velocity could be negative 25 meters per second. You can try this out. I will guarantee you will get 5.1 seconds. You don't get half the time because you're actually calculating the whole time of the trip, and you will get that. So that's kind of, two different ways to solve the same problem. You can either get half of the time, look at half the journey, and then double it, or you can look at the whole journey of this thing, and then that total time ends up being this same number. You would just have a different final velocity to put into this equation. So I hope that helps. Feel free to review this as needed.